Okay, welcome to this video on seismic waves. Understanding something about seismic waves is important, obviously, because seismic waves shake the ground during earthquakes, and this shaking causes damage. And what we can see here in the picture is a collapse of a freeway that happened during the 1989 Loma Prieta earthquake, and a number of people lost their lives when the upper deck of this freeway collapsed onto their cars. Now, it turns out that there are three different types of seismic waves, and so we're going to look at each one individually. And what we're going to do is we're going to start an earthquake on the fault that you can see right here. So what we're looking at here is a cross-section down through the earth, and this red line coming down is the fault. Now, we're going to record these seismic waves on something that's called a seismograph. And this is kind of an old school version of the seismograph, but it gives you a good idea of how these things work. So what we see here is a strip of paper on a rotating drum. And above that rotating drum, there's a pendulum with a heavy weight. And on the end of that pendulum, there's a pen. And so when an earthquake hits, and this pendulum shakes back and forth, it leaves a squiggly line on the piece of paper. And that records the seismic waves as they affect the seismograph. This white rectangle here, so this is essentially the sheet of paper on which we'll record the seismic waves as they come and hit the blue person here by the house. Okay, so we're going to start an earthquake right here. So the earthquake is going to begin right on the fault, right at that blue star or purple star. And it's important to remember that although there are three different types of waves, they all start at the same time. They're all generated at the same time. But the difference is that some of these waves move faster than other waves. And so you can imagine that if you're standing here by the house, you're going to first feel the waves that come the fastest, that move the fastest. Okay, so we're going to start off where there's no earthquake, and then now we're going to generate the earthquake. So I'm just going to draw a little star here to represent when the earthquake happens. And the first set of waves to hit are what are called the P waves. And I'm drawing the waves like a slinky, and you'll understand why in just a second. Okay, so those are the P waves. And here's the seismograph recording the arrival of those P waves. Now, they're called P waves because they're the first waves to hit, so they're the primary waves. So P just stands for primary, and they're the first ones to hit because they travel the fastest. And in fact, they travel around 6,000 meters per second. Just to give you an idea of what that is in miles per hour, that's about 13,000 miles per hour. So very, very fast. One of the reasons why they travel so quickly is that they travel through the earth, so they're transmitted very efficiently. And the reason why I drew this wave as kind of like a slinky is because these travel as longitudinal waves. And so just to give you an idea of what that means, imagine taking a slinky and instead of moving it up and down, you're pushing it back and forth. And as that slinky compresses, so we see an area here of compression, this area of compression is what moves. And so these are called longitudinal waves. And they're responsible for a low rumbling noise that alerts you to the fact that an earthquake is on its way. Okay, so these These are the P waves, and again, they're P waves because of primary waves, they're the first one to hit. The next set of waves to hit are the S waves, and the S waves travel like the regular types of waves that we're used to, in that they move up and down like that. On the seismograph, they look like this. They're responsible for more shaking than the P waves. The S waves, again, they're called S waves because they're secondary waves. They're the second set of waves to hit. And they hit after the P waves because they move more slowly. So they move about at half the speed of the P waves, so about 3,000 meters per second. And like I've drawn here, these are transverse waves, so they're like ocean waves. They're also rather quick because they travel through the Earth. But they do result in some shaking, and they are somewhat damaging. Now the next set of waves that you would feel are the surface waves. And as the name implies, these travel along the surface. And so if we're looking at the seismograph, when the surface waves hit, this is where the seismograph really starts to go crazy. Now the surface waves, you feel them after the secondary waves because they move the slowest, but also because they move the slowest, they're the most damaging. And also they're the most damaging because they travel on the surface. And so when you look at damage from an earthquake, it's primarily from the surface waves. Now the seismograph isn't just useful to help us distinguish between these three different waves, but it's also what gives rise to the Richter scale. So for example, if you've heard of, an earthquake that was a 6.9 on the Richter scale, you might have wondered where that 6.9 might have come from. Well, it just literally comes from the height of the wave on the seismograph. So here's a typical seismograph. Like we saw before, you have the P waves, they hit first, then the S waves, they hit second, and then the surface waves hit last, and the highest peak on the surface wave is what gives us the value for the Richter scale. So for example, this earthquake here would be a 1.9. Now you might think, oh well, a 2.0 is only twice as strong as a 1.0 because we're used to thinking of scales like that. But in fact, that's not true. Each whole number increase results in 30 times more energy released. So to go from a 1 to a 2, a 2 is 30 times more powerful. Or if you were to look at an example, a 6.0 is 30 times more powerful than a 5.0. And what this means, if it's a 30 time increase for each number, a 7.0 is 900 times more powerful than a 5.0. And this is important because a lot of times people think, oh, well, if we have a lot of small earthquakes, that releases the energy of one large earthquake, but in fact, that's not true. So it would take 900 5.0s to release the energy of a 7.0. So the Richter scale tells us something about the energy release, but when it comes to natural hazards, what we really care about is the amount of shaking. And so that leads us to the Mercalli scale. So the Mercalli scale tells us something about the shaking intensity. And in the slide presentations, I go into the Mercalli scale in a little bit more detail, but for now, just understand that the Mercalli scale tells us something about how much shaking there is. And what we're going to learn about in just a second is that the intensity of the shaking depends a lot on the properties of the ground. In other words, what is the ground composed of? And it's important to know that because waves travel quickly through strong material, but seismic waves travel slowly through weak material. And that's important because the magnitude of the wave, so the hotter the wave, is inversely proportional to the velocity of the wave. So let's take a look at an example to see what that means. So we have two different situations. We have two poorly drawn houses. One is on hard bedrock, so for example granite, and the one on the right is on mud. So mud is basically the weakest material there is when it comes to the ground. So let's generate an earthquake right here. And remember, waves travel quickly through strong material, and then the magnitude of the wave is inversely proportional to the velocity of the wave. So the wave, the seismic wave, is going to travel quickly through the bedrock, through the granite, and the magnitude of the wave is going to be relatively low because it's traveling quickly. Now let's look at the opposite situation where we have the seismic wave traveling through the mud. It's only going to travel very slowly through the mud, and as a result, the amplitude of the wave is going to be much higher. And so you can imagine then that with this amplitude of the wave much higher, shaking at the surface is going to be much greater than it was with the hard bedrock, with the granite. And we saw this effect very clearly during the Loma Prieta earthquake. The epicenter was about where the black star is right here that I just circled in purple. And these colors represent shaking intensity. So blue is less shaking, and then red is more shaking. And so what you'll notice is as we travel from the epicenter to the north, the shaking, first of all, isn't that bad because this is a lot of bedrock. In fact, there's granite through here. And we see the shaking also decreasing as we move away from the epicenter, which makes sense. But then once we hit San Francisco, the shaking cranks up again. And the reason for that is that San Francisco is essentially built on, a lot of it is sand, and right by the bay, it's sand that's obviously going to be relatively wet. We see also the same kind of situation here in Oakland and Berkeley, where right along the bay, where you have mud, wet mud, the shaking was pretty intense. So we're going to zoom in on this San Francisco and Berkeley area. And again, notice these pockets of intense shaking right along the bay. And this is where we saw some of the worst damage during the Loma Prieta earthquake. Where that freeway collapsed, that was right around here, right around the reds and the yellows. And the reds here in San Francisco, this was what's called the Marina District, and that's where we saw some of the worst damage in San Francisco. So what's interesting about this is that the ground properties are actually more important than the distance from the epicenter when it comes to shaking. Okay, well, thank you for your attention. I hope that was useful.